Welcome back to another tutorial on business statistics in Excel. Today I'm going to explain sampling distribution and how we tackle questions regarding this topic. In many applications, we are interested in some characteristic of the population, like the average height of the population or the proportion of the population with the specific features. In that case, studying the population will be time-taking, needs a lot of money and availability of the data, which most of the case we don't afford that. So instead of studying the population, we take sample from population, study the sample, and with some level of confidence, we claim our understanding about the population. Let's assume that we are interested in understanding the height of the population. We have the target population with a distribution over the height. We call this population distribution. Most of the time, if the population is so large, this distribution is normal. Then we take sample of size n is here 5 people from the population. We can build a distribution over the height of these people, and we call that distribution sample distribution. Sample distribution is the frequency distribution of the height of people within one single sample. If we continue taking multiple samples, each of size n, and n here is 5, first we calculate the average of height in each sample by adding up the height of these people and then divide it by the number of items, which is 5 here, and we get the average height of each sample. Then we can build the distribution over these averages, and we call them sampling distribution of sample mean. Note that sampling distribution is a frequency distribution over multiple samples. The sampling processes starts with identifying the target population and then take random sample and measure the target variable of each individual in the sample and calculate the average of the height of the people in that sample. Then we can put that average on the frequency distribution. We can repeat this process for many times to build that sampling distribution. For example, the second sample, we have these measures for the height of the people. Then we calculate the x-bar or the average height within the sample and we put it into frequency distribution. So again, we can repeat this multiple times so that we build this frequency distribution, which we call sampling distribution. So if our sample size is large enough and we keep sampling, we can build a sampling distribution, which most of the time is normal distribution. Let's recap the concept. We have population distribution, which is a frequency distribution built on the whole population we have. Then we can build sample distribution, the distribution of the height of these people within one single sample. And if we take multiple samples and calculate the average height of each sample, and we put these averages on the distribution, we build sampling distribution. Now let's discuss the relationship between sampling distribution and population distribution in terms of mathematical formulation. So we have this population distribution that most of the time is normal with the average of mu or mean of mu and a standard deviation of sigma. So x is the random variable, like the height of people in the population, which is normally distributed with a mean of mu and a standard deviation of sigma. So we take samples from this population and we build sampling distribution. Now random variable is average height because we are calculating the average height of people in each sample and then put that average within sampling distribution. So the random variable is x-bar or average height of the people within samples. Mean is defined by mu sub x-bar or expected value of x-bar, and standard error sigma sub x-bar, which is equal to sigma over root square of n. Note that the average of sampling distribution is same as the average of population. So mu sub x bar is same as mu. However, standard deviation is the standard deviation of the population divided by the sample size. The sampling distribution is narrower than population distribution, and as we increase n, the standard deviation will decrease, meaning that this distribution gets narrower and narrower, and that means that most of the samples are close as possible to the average of the population. And that is the base for the central limit theorem. As we increase the sample size, the distribution of sampling distribution gets closer to the normal distribution and also gets narrower and narrower, meaning that we have a better estimation of the population mean using those samples. So central limit theorem says for the sampling distribution of mean, if sample size is more than 30, then sampling distribution is normal, and we can use the normal distribution features to answer any probability question. Now let's see how we are going to use the concept of sampling distribution of mean in order to solve some of the probability question. These are the steps you need to take in order to answer the problems. Step 1, you will need to check if the sampling distribution is normal. There are two conditions. Either the population should be normal, then we are 100% sure that sampling distribution is normal, or the sample size should be more than 30, therefore sampling distribution of mean is normal. Step 2, given the expected value and a standard deviation of the population, we will update the features or the mean or standard deviation of the sampling distribution of mean. If the population mean is denoted by mu, then we know that sample mean also is mu. And population standard deviation is sigma, then sample standard error or sigma sub x bar is sigma over root square of n. Next step, formulate the target probability, and last step, calculate the z-score and find the target probability, or use the Excel function to calculate the probability. Let's look at this example. Suppose it's known that the height of American adult follows a normal distribution with a mean of 160 centimeter and a standard deviation of 7 centimeters. What is the probability that the average height of 10 random Americans is less than 157? So we know that population distribution is normal, therefore sampling distribution is also normal. The population distribution has a mean of 160 and a standard deviation of 7. Therefore, we can update the features for sampling distribution as well by taking 10 samples. That's the sample size. The average of the sample mean, or mu sub x bar, is 160, same as mean. And a standard deviation of sampling distribution, sigma sub x bar, is equal to sigma over root square of n, or 7 divided by root square of 10, which is basically 2.21. Now, we are looking at the probability that average height of the Americans is less than 157 centimeter. In another word, if this is the sampling distribution, we are looking at this blue area showing that x bar, or the average height, is less than 157. Let's look at this example in the Excel. So we have a population which is normal, and mu or mean of that population is equal to 160. Sigma is equal to 7. We take a sample. That sample mean E of x bar is same as the mean or mu, and S of x bar or sigma sub x bar is equal to 7 divided by a square root of n, which n is 10. So I can write down n here too, sample of 10, and then put it in that function too. So instead of 10, I choose this cell, 2.21. So step 1, the sampling distribution of mean is normal because population is normal. So that's step 1. Step 2, update the features of the sample, which we did here. Step 3, formulate the probability, and step 4, calculate the probability. So I'm going to put these 2 steps together. The probability that average height is less than 157, that's equal to norm dot dist 157, comma, the mean of the sampling distribution, the standard deviation of sampling distribution, and always true. So that is the probability that the average height is less than 157. Let's calculate the probability that the average height is more than 170. So instead of less than 157, we are looking at this blue area, more than 170. So I am looking for the probability that X bar is more than 170. So more than 170 gives us this blue area, which is on the right side, but norm.this always gives us the left side area. So in order to answer to this question, I need to transform it to any form of less than equal. That is equal to 1 minus probability of X bar less than 170. And that's because either X bar is more than 170 or less than 170, and the area under the curve is 1, meaning that the summation of this blue area and red area is 100%. Therefore, one part is 1 minus the other part. So I can calculate that as 1 minus norm.dist 170, mean of the sampling distribution, standard deviation, and always true. So there is a very small area or a small chance that the average height is more than 170. Let's look at the probability that X bar is more than 165. That's equal to 1 minus probability of X bar less than 165. We can use norm.dist equal to 1 minus norm.dist 165, the mean, the standard deviation, and true. So there is 1% chance that the average height is more than 165. Let's look at this example. A haunted house manager claims that the average time a visitor spent in a haunted house is 45 minutes with a standard deviation of 8 minutes. To check this claim, a simple random sample of 35 visitors is taken. What is the probability that the average time spent in the haunted house by the sample of visitors will be between 43 and 47 minutes? So we have a population. The average of the population is given to us 45 minutes. By the way, we need to also define X. The random variable is the average time spent in the haunted house. Average is 45 and standard deviation or sigma is 8 minutes. So we take a sample of size 35. The average of the sample, or E of X bar, is equal to the mean of the population, and S of X bar is equal to sigma over root square of n, and n is 35. So step 1 is identifying whether the sampling distribution is normal. Sampling distribution is normal because n is more than 30. So according to the central limit theorem, if n is more than or equal to 30, then sampling distribution is normal. Here n is 35, therefore sampling distribution is normal. Step 2, update the features for the sample, which we already did. The mean and a standard deviation for sampling distribution is updated. Step 3, formulate the probability, and step 4, calculate the probability. So I'm going to highlight these cells. Step 3, formulate the probability. What is the probability that x bar is between 43 and 47? So basically we are looking at this area. We have a normal distribution for sampling distribution, average is 45, and we are looking at this gray shaded area. So in order to calculate this between area, we need to reconstruct this probability function. So probability of x being within some area is the probability that x is less than the larger number minus the probability that x is less than smaller number. So this gives me basically this small white area, and the first part gives me the area before 47, the whole left area. So if I subtract this small white area from the whole left area, it gives me the between area. So now I can rewrite the Excel function equals to norm.dist 47, mean is 45, standard deviation is 1.35, true because it's cumulative, minus norm.dist 43, mean of the sampling distribution, standard deviation, and true. So there is 86% chance that the average spending time in haunted house is between 43 minutes and 47 minutes. I hope this clarified the sampling distribution for the mean. In the next tutorial, I'm going to talk about sampling distribution of population proportion.